Hello students, today our topic is function generator. So it is represented by a pin number ICL8038. So what is a function generator? A function generators are designed to provide the basic waveforms such as square wave, triangle wave and sine wave. The ICL8038 is a function generator chip capable of generating triangular, square, sine, pulse and sawtooth waveforms. They are also called as waveform generators. In function generator, VCO generates the triangular and square waves. The triangular waves is passed through the on-chip wave sharper to generate a sine wave. Hence, this is the circuit diagram of a ICL8038 function generator. Before going into this circuit diagram, let us see what is actually a function generator and how does it actually works. So, as already told, function generators are designed to provide the basic waveform such as square wave, triangle wave and sine wave. They are also called as waveform generators. The monolithic function generator provides these basic waveforms with a minimum number of external components, reducing complexity but increasing the reliability of the circuit. They find application in communication, telemetry, electronic music, and testing and calibration in the laboratory. In function generators, VCO, voltage control oscillator, generates the triangular and square waves. The triangular wave is then passed through the on-chip wave sharper to generate a sine wave. The sawtooth and pulse waveforms are generated by configuring the oscillator for a highly asymmetric duty cycle. So, in this section, we will discuss the ICL8038 precision function generator from Intercell. So, this is the circuit diagram of an ICL8038 function generator. It has capacitors and resistors interconnected. So all these resistors, simplifying it into a block diagram, we may obtain a comparator. So inside this we may have a comparator CMP1 and CMP2 and also a buffer, a wave shaper. So simplifying it into a block diagram, we may take the following, we may obtain this following notes. The circuit needs a dual power supply, A plus 15 or minus 15 power supply. The frequency of the output waveform can be adjusted using R7. It must be a 100K log pot. The duty cycle can be adjusted using R3, a 1K pot. The distortion of the waveform can be adjusted using R5, a 100K pot. So square, triangle or sine waveforms can be obtained simultaneously at pin 9, 3, 2 respectively. So this is the pin diagram. So here we have 1 to 14 pins. So the first one is sine wave adjust, second one is the sine wave out, third one is triangle out, fourth one and fifth one is duty cycle frequency adjust, sixth one is voltage plus, seventh one is FM bias, eighth one is NC no connection, ninth one is no connection, sine wave adjust, we are ground, timing capacitor, square wave out, FM sweep out. So now let us look into the basic principle and operation of an function generator, ICL8038. So it is very easy to understand the working principle of a ICL8038 function generator using its simplified block diagram. The operation of ICL8038 is based on charging and discharging of a grounded capacitor, whose charging and discharging rates are controlled by programmable current generators IA and IB respectively. When switch is at position A, the capacitor charges at a rate determined by current source IA. When the capacitor voltage reaches the switch position to change from position A to B, then the capacitor starts discharging determined by the current. Once the capacitor reaches the voltage, the lower comparator triggers and sets the flip-flop out. Here inside the ICL we may have a flip-flop. This causes the switch position to change from one position to the other position, hence the cycle repeats. So here we use a RS flip-flop. As a result, we get a square wave at the output of the flip-flop and a triangular wave at the across the capacitor. So the triangular wave is then passed through the Thorne chip wave shaper to generate the sine wave. To allow automatic frequency control, current IA and IB are made programmable through an external control voltage. For equal magnitudes of current IA and IB, output waveforms are symmetrical. Conversely, when two currents are unequal, output waveforms are symmetrical. By making one of the currents much larger than the other, we can get sawtooth waveform across capacitor and rectangular wave at the output of flip-flop. So transistors Q1 and Q2 form programmable current sources whose magnitudes are set by external resistors RA and RB. These current sources are driven by emitter follower. It also compensates base emitter voltage drop for Q1 and Q2 to ensure the voltage across RA and the voltage across RB is equal to the input voltage. So thus the current across A and the current across B can be given as VI by RA and VI by RB. So the current IA controls the charging rate of capacitor while the current IB is diverted to current minor, where it undergoes a polarity reversal as well as amplification due to the combined action of Q5 and Q6. This results in a current swing magnitude of 2IB. The voltage across capacitor is applied to the Schmitt trigger. The Schmitt trigger is similar to that of a IC555 timer. So the upper comparator has a voltage of 2 by 3 VCC and the lower comparator has 1 by 3 VCC. Transistor Q7 acts as a switch. When the output of the flip-flop is high, Q7 saturates and pull the base of Q5 and Q6 low and thus shutting off the current sink. As a result, the capacitor starts charging at a rate set by the current IA. Once the capacitor voltage reaches 2 by 3 VCCs, comparator 1 triggers and clears the flip-flop, thus turning Q7 off. This enables current mirror to sync current equals to 2IB so that the net current flowing out of the capacitor is IL is equal to 2IB minus IA. This causes capacitor to discharge. Once capacitor voltage reaches 1 by 3 VCC, CMP2 triggers and sets the flip-flop and action repeats. It is important to note that net current flowing out of capacitor C should be positive. That is 2IB minus IA is greater than 0, discharging capacitor, and hence 2IB is greater than IA. So this is the charging and discharging of a capacitor functional generator ICL 308. So whereby the frequency of the output waveform we can find out as F out is equal to 1 by T. Here the timing is charging and discharging time, so DC plus DD. Hence the overall percentage of D we get is equal to duty cycle is 1 minus RB by 2 RA into 100, where RA is equal to RB, that is duty cycle is 50%, and we get symmetric waveforms. For asymmetric waveforms, the RA is equal to RB, therefore F out is equal to 1.5 times of VI divided by CRA VCC. So this VCC, this 8038 can be used in communication, telemetry, electronic music, testing and calibration in the laboratory. So it has a duty cycle of 2% to 98%, which is the most efficient of all. Thank you.